Yesterday, did I show you this bottle of purple stuff?
Yeah. Yes.
Okay, so is it currently changing color? So what do we know about it? It's at equilibrium, right? If you take a look at the very top of your page, you see a pretty weird-looking chemical reaction, one the likes of which you have not seen before, because you have square brackets thrown in there. It's what we call those square bracket ions, like the cobalt 6 waters plus 2 charge. This is called a complex ion, because it's pretty complex. Not real imaginative naming, I know. But the idea here is you don't need to worry about the chemistry so much, is that know that the cobalt water complex ion is pink in color, and the cobalt chloride complex ion is blue in color. And in this bottle, we currently have both. And seeing as it's kind of purplish, we probably have about equal concentrations of both while it's at equilibrium. But remember, equilibrium doesn't mean equal amounts. It means an equal rate of reaction. Remember, if this isn't changing color, then that means the forward reaction, the reaction that's taking the pink stuff and turning it into blue stuff, is happening at the same rate as the reaction where blue stuff is turning into pink stuff. Correct? Give me a thumbs up, down, sideways if you can see how it relates to yesterday. Okay? Which means, as we learned yesterday, we could add things and cause stresses to this equilibrium to change it to a new equilibrium. And you'll see I have some test tubes here where, if we take a look, I've got a blue one and a pink one, and they're not changing color either, are they? Okay, so this is at equilibrium, and this is at equilibrium. It's just that this one at equilibrium has a whole lot of this stuff and not very much of this stuff. So that every time the reaction going this way turns a blue ion to a pink one, well, it gets undone immediately. So it doesn't change color. Same thing is true here. Now we have a whole bunch of pink stuff. Any pink ions that become blue ions immediately become pink ions again at the same rate. So we don't see change. Equilibrium, equilibrium, equilibrium. Okay? So the idea today is we are going to take samples of this system at equilibrium, and we're going to apply stresses to it and see what color it changes. We're also going to learn how to, if I just tell you what the stress is going to be, you can predict what color it will change. And that's really what we're doing again tomorrow in tomorrow's lab. So we've got a few days of this. What I've written here on the board, on the left-hand side here, is the kind of the steps you want to follow when you're filling out these tables. And I'm going to be modeling that as I go along. It doesn't go left to right. It jumps around. So just kind of follow along as we do that. So the first thing I'm going to do is I am going to take and add heat. Adding heat is going to be my first stress. I'm going to take a test tube full of it. I'm going to put it in the Bunsen burner and see what happens. But let's fill this out first. According to my directions here, the first thing I want to do is take what we've written here as our stress and turn that into an arrow that we circle to show that this is what we are going to be doing. I'm going to add heat to the system. We haven't often included the word heat in our chemical reactions, but we've included it there. So the forward reaction, the reaction that goes from left to right, heat is a reactant in that reaction, correct? Does that make it endothermic or exothermic? None of you sound certain. Raise your hand if you think it's endothermic. Raise your hand if you think it's exothermic. Raise your hand if you have no idea. Okay. It's endothermic. Remember what we talked about with endothermic reactions. Endothermic reactions require an input of heat. So you can think of heat as a reactant in that reaction. So for the pink stuff to turn blue, we need to have the pink ions around, we need to have chloride ions around, and we need to have heat. Otherwise it won't happen at all. Okay? What does that mean about the reverse reaction? In the reverse reaction, if I were to write it from right to left, this plus this would make this, this, and heat. So if heat is a product of the reaction, what is the reverse reaction? Exothermic. Thumbs up, down, sideways if this makes sense. Okay. All right, so now what we have to do is determine which rate we're affecting. You only affect the rate that the thing you're talking about is a reactant of. And I know that's horrible grammar because I just ended the sentence in a preposition. So in which reaction is heat a reactant? The forward or the reverse? Forward. If I'm increasing the heat, what would I do to the speed of the forward reaction? I'd increase it. So I'm going to increase the forward rate, and this is important, a lot of people don't get this. I'm doing nothing to the reverse rate. Because the reverse rate simply needs water and cobalt chloride to collide. It does not need an input of heat. So by adding more heat, I'm not doing anything to what this is doing. Yes?
If the equation doesn't specify if it's which side is heat on, should we say both of them go on, or just the forward?
Well, when we do it, heat will always be part of it. Well, because in all of these reactions, one is exo and one is endo.
Okay.
So that, yeah. All right? The next thing we do is predict the shift. So what I'm going to say is this. Don't write this yet. It's at equilibrium right now, correct? So therefore, I would draw the arrows to be the same length. But I'm going to change that. Once I've applied this stress, how should I draw these arrows? Which one should be smaller? The reverse reaction should be smaller. I'm doing nothing to the reverse rate, but the comparative rate makes the reverse rate smaller than the forward rate. The forward rate is now faster than the reverse rate. That's what you have to get here, is that whichever rate is faster should get a longer arrow. Thumbs up, down, sideways, if that makes sense. Now here's the trick. And you might have to think back to the peanut butter and jelly analogy yesterday. So if my wife has peanut butter jelly bread and she's making sandwiches, as she's making them, these amounts go down and the sandwich amounts go up, correct? The kid's unmaking them, this goes down and these go up, correct? Okay, so now, if they're not happening at the same rate, the forward reaction, I'm going to use these up and make these faster than these get made and these get replenished. So that means the amount of pink and chloride will go down and the amount of blue and water will go up.
Sure.
Do I need to say that again?
Yeah.
Okay. Think about it this way. We've just said that the reaction is... One way of saying this is that the reaction shifts to the right, or it shifts to the product of the forward reaction. That means that I'm going to make these things faster than I unmake them. If I'm making them faster than I unmake them, I'm going to get more of these than I had before. And if I'm using these up faster than I'm replenishing them, I'm going to have less of them. Does that make sense? Okay. Now, we need to look at the two things that have color and see what's happening. I'm increasing the concentration of the blue stuff. I'm decreasing the concentration of the pink stuff. What color should it turn? Should turn blue. Well, let's see if that happens. So I will take a pink one. And I will light a Bunsen burner. And I've turned it blue. Oops, starting to boil. Gotta stop. Okay, is it changing color right now? It's back at equilibrium, but now at a new equilibrium. How could I turn it back pink?
Freeze it?
What did you say first, Ekram?
Wait.
Could wait, it'll cool down slowly, right? Or I could speed up the process by freezing it, but we couldn't watch that. Take a look around you. What could I do? Put it in the ice water bath. Very good. So if I put it in the ice water bath, it'll take a while. Let's think about what that stress is. How would I name that stress? Faith?
Would you say
I would say removing heat. Where would I draw a circled arrow, Heidi?
the heat and it will go down the circle?
Good. Locale, which rate am I affecting, the forward rate or the reverse rate?
Reverse.
No. Even though we're decreasing the amount of heat, it's still the forward reaction that we're changing. We're just making it slower now instead of faster, right? So once again, is heat a reactant in the forward reaction or the reverse reaction? Then that's the one that we're changing, but we're decreasing it. So what are we doing to the forward reaction? We're slowing it down, right? What are we doing to the reverse reaction? How do you say nothing in Italian?
Niente.
Niente. There you go. So you got to actually use Italian in class. Now you get your extra credit. All right. Talk to a neighbor. What should these arrows look like?
Wait, is this from the
From the blue. You missed a great day.
My wife. Well,
You missed the wrong day. You have not watched your late night TV, have you?
No, I don't know TV. I don't have time for that.
All right, Claire, what you got?
The top one is small and then the bottom one is
Let's don't talk about top and bottom. Let's talk about forward and reverse.
the forward reaction is the smaller arrow, and the reverse reaction.
Yeah. Because you could put the reverse reaction on top and the forward reaction. It doesn't matter, right? Some people do that. So talk about the forward reverse reaction. All right. So which way does this shift then? To the left or to the right? Which way is it pointing? Which way is the bigger arrow pointing? To the left. So if it's shifting to the left, that means that this reaction is going faster than this reaction is. So what's going to happen to pink and chloride? Going to increase. What's going to happen to blue and water? So what color should it turn if pink is increasing and blue is decreasing? Anyone take a look into the beaker over there? It's pink again. Woo! See it? Okay. Thumbs up, down, sideways so far. Okay. I'm going to add hydrochloric acid. Is hydrochloric acid one of my chemicals in this? No. What am I doing then in terms of things in there? Noah? I'm adding chloride ions. So that's my stress. I'm going to add chloride ions. Right now, with a partner, complete the row. Okay. Ashley, got it?
I think so.
Tell me in the order that we do it. So don't go left to right. Do the order that we've been doing it.
So the chloride goes up, it increases,
Okay.
and then that affects the forward rate. So the forward rate, and then
Yeah.
the forward rate increases, and the reverse rate is not affected.
Okay.
And then it's shifted to the right.
Yes.
And the heat and the other two reactants are decreased. And the two products are increased. And the color.
Correct.
Oh wait, but you.
Some of you got this wrong. I was watching you.
Yeah. Yeah.
Okay. My guess would be, and from what I saw, most people got this correct. Did you get the shift right?
Yeah.
Yeah.
Okay, so what you're doing is you're not interpreting that correctly. So pay attention here for a second if you had trouble with this. What you're saying, if you're saying it shifts to the right, is that the forward reaction is going faster than the reverse reaction, correct? That means that these two things are being used up to make these two things faster than these two things are being used up to make those two things. So these are being used faster than they're being replenished. These are being made faster than they're being used. Therefore, these go up because you're making them faster than you're using them. These go down because you're using them faster than you're making them. Thumbs up, down, sideways. So it turns blue because the concentration of the blue stuff goes up and the concentration of the pink stuff goes down. Stephanie?
Why is the heat?
Because the forward reaction is endothermic, the reverse reaction is exothermic, and it's the same amount of heat both ways, the enthalpies are the same, but because this is going faster, there's a net loss, or a net absorption of heat versus a net release of heat. So the heat will go down because it's going to remove heat from the system. Let's do it. So if we think it's going to turn blue, I should start with a pink one, right? Okay, here we go. When do I have until 05? Are we sure it's 05?
Pretty sure.
Okay, here we go. Happens pretty quickly. Life misses it. You miss life if you don't pay attention. Didn't Ferris Bueller say that? That's blue. Okay. How can I make it pink? Without adding heat. Ben? Why would adding H2O turn it pink? Go through the whole thing.
So by adding that, it would be increasing the rate of the reverse reaction.
This time, this is different than we've done before. We're increasing the rate of the reverse reaction. Are we doing anything to the forward reaction? No. So how would I draw my shift arrows?
You draw the reverse reaction arrow bigger than the forward reaction arrow.
So I'm shifting it to the left.
Yeah.
Okay. The response to that would be what?
Less CO, Cl4.
Less blue.
And then increase heat, increase chlorine ions, and CO2 HO6.
Okay. So that means pink concentration going up, blue concentration going down. This is an easy one to do. We have water all over the place, don't we? So the one that I just turned blue, all I have to do is, everyone watching, you guys are going to miss it. Turn pink. Life is good? Okay. I'm going to tell you there's another way that you can stress these systems. We removed heat. It is possible sometimes to remove other things. If I wanted to remove water, how could I remove water? I could boil it. However, in test tubes, that's not practical because it would just shoot out of the test tube and I'd hurt myself or one of you. Not an option. Can I remove chloride ions? No?
Didn't you add something that's not soluble with chloride?
So we would add something that would form an insoluble precipitate with the chloride ions that would bind the chloride ions and keep them out of the solution. Because right now the chloride ions are bouncing around, they're aqueous, they're bouncing around in solution. If we bind them into a crystal, they fall to the ground and they can't take part of this equilibrium anymore. So going back to what you know of solubility rules, propose something I can add. Ekram says silver. Would silver work? Silver chloride, is that soluble or insoluble? Insoluble. I would agree. What else would work?
Tungsten.
I'm not sure about that. I don't know my tungsten solubility rules. On our solubility rules, there were 3 exceptions to the halogen rule. Lead, mercury, right? So
Solid effort.
we're going to go with what Ekram proposed because I happen to have some silver nitrate here. Okay? So how would we write this out, though? Is silver in my equilibrium? No. So what is the stress that I'm doing? Removing chloride. Ish. You're up.
So it would, you're adding the silver nitrate but using phosphorus. Would it increase the forward rate?
Hold on. I'm removing Cl.
Yeah,
So I have to, first thing I have to do is put a circular arrow.
draw a line going down and see how it circle it.
Okay. So now, which is it, the forward or the reverse rate that I'm affecting? That's the first question to ask.
The forward.
Correct. If I'm removing something it needs to go fast, am I speeding it up or slowing it down?
Slowing it down.
Correct. What am I doing to the reverse rate?
Nothing.
Okay, so ish, how does it shift?
So then the forward reaction would shift to the right.
So we just said the forward rate is now slower than the reverse rate. So it's going to shift to the left. Do you see that? You really have to pay attention to what that means, right? You're a track guy, right?
Yes.
Okay, so remember what we talked about yesterday with Faith and I running, right? I could beat you in a sprint, but only if I kicked you in the back of the leg first. But that wouldn't make me faster, it would just make you slower. Right? So what's the response to that then?
So then with the COH2O, that would go up.
This would go up, what would heat do?
It would also go up.
Correct.
as well.
And what would the blue stuff in the water do?
Go down.
So what color would this turn?
So it would turn.
It would turn pink. Let's see. Now this will be different than the other ones because it won't just turn pink, it'll turn pink and cloudy because we're forming a precipitate, correct? That makes sense? And I will tell you that it is not a pronounced pink as the other ones, but you'll see that there is some pink going on. Right? It's hard to see, it looks white, but you see that there's a little bit of pink color in there? Yep. All right.